point a camera at a page and take the photograph. Now look at what came back. The page is a rectangle. You know it is, you're holding it. But in the picture, the two long edges aren't parallel anymore. They lean towards each other, and if you followed them off the edge of the frame, they'd meet. Something took a flat rectangle and did that to it. What? A camera turns 3 numbers into 2. Every point in front of it sits somewhere in space, 3 coordinates, X, Y, and Z. And the camera hands you back 2, which pixel it landed on. The third one, the depth, is gone. Not hidden, thrown away. And normally that's fatal. Give me a point in one photograph. Ask me where that same point lands in a second photograph taken from somewhere else, and I can't tell you. Not because the maths is hard, because the answer depends on how far away the thing was, and the photograph didn't keep that number. Unless everything you care about is flat. A page has no depth of its own. Every point on it, every letter, every corner, lies on one single plane. And the moment that's true, the missing third number stops being missing. The plane itself tells you what it was. So the impossible map becomes a possible one. One 3x3 matrix, 9 numbers, and one of them is free, so really 8. And it maps every point of that plane from one photograph into the other. Not the 4 corners, every point. That matrix is called a homography. 8 numbers is a small enough price that 4 pairs of matching points pay it exactly. And it's what your phone is doing when it turns a photo of a page into a scan. By the end of this, you'll derive it yourself, from 4 point pairs and a cross product.
Here's the whole thing in one line, and then 12 minutes on where it comes from. X prime is similar to HX. One 3x3 matrix, and it maps every point on a flat surface from one view to another. Not the 4 corners you dragged. All of them. That single line is a document scanner. It's a panorama stitched from 2 shots. It's the offside line a broadcaster paints onto a football pitch, and it's the printed square that tells a phone where it is in the room. 4 products. 1 equation with a different H. And I want to be honest before we start. A homography is not a warp you tune until it looks right. It is 8 numbers and 4 point pairs determine them exactly. Everything that follows is proving that sentence.
First, what kind of thing is H? Because matrix isn't an answer. Start with a translation. 2 numbers, so 2 degrees of freedom. Slide the square about and it keeps its lengths, its angles, its parallel sides. Add a rotation and you have a rigid transform, 3 degrees of freedom, still the same lengths, still the same angles. Add a scale, that's a similarity, 4 degrees of freedom. Now lengths are gone, angles survive. Add a shear and you have an affine transform, 6 degrees of freedom, and now angles are gone too. What's left is that parallel lines stay parallel. And then you add 2 more numbers. The bottom row of the matrix stops being 0, 0, 1, and parallel lines stop being parallel. That's a projective transform, a homography, and it has 8 degrees of freedom. Look at what survives all the way down. A straight line stays straight. That is the only promise a homography makes. Everything else, length, angle, parallelism, has been given away in exchange for degrees of freedom. At the start, I told you a flat scene rescues the depth the camera threw away. I owe you the algebra, because why it works is the part that tells you when it stops working. Here is a general relation between 2 views written out, and there, sitting in the middle of it, is a z, the depth. Not one z, a different z for every single point in the image. That is precisely what a matrix cannot do. A matrix applies the same 9 numbers to everything you feed it. So watch what a plane does to that z, because then the depth isn't free anymore. A plane is exactly the statement that n transpose x equals d. Given the direction you're looking, the plane tells you the distance. Substitute that in and watch what happens. The z cancels, and what's left is a single 3x3 matrix built out of the rotation, the translation, the plane's normal, and its distance. That's the homography, and that's where it comes from. One footnote, and it matters in practice. If the camera only rotates, if t is 0, the translation term vanishes and you don't need a plane at all. That's why panoramas work on any scene as long as you don't walk sideways while shooting.
So how many point pairs do you need? Count. H is 3x3, 9 numbers. But look at that similar to sign. I've been writing it deliberately. X prime is similar to hx, not equal to it. They point the same way, they can differ by a scale. Which means if I multiply the whole of h by any non-zero number, nothing changes. The third coordinate divides it straight back out. So one of those 9 numbers is free. It's not information, it's just how you happen to write it down. 9 minus 1. 8 degrees of freedom. Now the other side. 1 point pair, a point here, the matching point there. How many equations is it worth? 2. And in a minute, I'll show you why it's 2 and not 3, because that's the part people get wrong. 8 unknowns, 2 equations each, 4 point pairs. And one condition that sounds fussy and is not. No 3 of them may lie on a line. Right, 4 pairs, 8 numbers. Let's actually solve it. Start with the obvious thing and then notice it's wrong. X prime equals hx is false. It's only true up to that scale factor we just talked about, and we don't know what the scale factor is. So we can't use an equal sign, and we can't solve an equation we can't write down. Here's the move. 2 vectors point the same way exactly when their cross product is 0. Not roughly 0, exactly 0. And it doesn't care what the scale is. So write it that way. X prime cross hx equals 0. The unknown scale is gone. And look at what kind of equation this is now. Every entry of h appears linearly. That's why this ends in a matrix solve instead of an optimizer. Now expand the cross product. You get 3 rows. And here is the step almost every explanation skips. Look at the third row. It is x prime times the first row plus y prime times the second. It is a combination of the other 2. It carries no information at all, so throw it away. 2 equations per point pair, not 3. And that is why 4 pairs is exactly enough rather than 3, and why nobody needs a 5th. Write those 2 rows out. 9 columns because there are 9 entries of h stacked into one long vector called h. Do it for all 4 pairs, stack them, and you have an 8x9 matrix A, and the statement AH equals 0. One problem, h equals 0 solves that. It also tells you nothing. So we ask for the smallest AH we can get while insisting h has length 1. You can't shrink your way out of it. And that problem has a name and a one-line answer. H is the smallest right singular vector of A, 1SVD. Reshape those 9 numbers into 3x3, and that is your homography. Let's write that matrix out properly, because it's the thing you'll actually type. 2 rows per correspondence. Minus x, minus y, minus 1. 3 zeros. Then x times x prime, y times x prime, x prime. And the second row is the same shape, shifted. 3 zeros first, then the y version. Now do that for the second pair, the third, the fourth, and there it is. 8 rows, 9 columns. AH equals 0. 9 unknowns, 8 equations. 1 short, and that is not a mistake. It's the scale freedom we've been talking about since the start. We get to spin that missing equation however we like. And there are 2 honest ways to spin it. The first is the one we just did. Insist that h has length 1. That's the homogeneous route. Minimize AH, and the SVD hands you the answer. The second is more obvious, and it's what a lot of people reach for first. Just set h 3 equal to 1.
Then the 9th column moves to the right-hand side, and what's left is an ordinary 8x8 AX equals B. Pseudo-inverse, least squares, done. And I want to be fair here, because this is where explanations usually get lazy. On an ordinary homography, those two give you the same answer, both exact to machine precision. Setting H33 to 1 is not a mistake, but ask what it assumes. It assumes the true H can be rescaled so its corner entry is 1. And there's exactly one value where that's impossible, when H33 is 0. What does that mean geometrically? Put the origin of your source image through H. You get H13, H23, and 0 on the bottom. A 0 in the homogeneous coordinate is a point at infinity. So H33 equals 0 just means the origin of your first image lands on the horizon of the second. That is an ordinary photograph, not a pathological one. So let's run both on exactly that case. The SVD, error of 10 to the minus 10 pixels, perfect. The H33 equals 1 route, 6.5 pixels. And here's the part that should bother you. It doesn't fail loudly, no exception, no warning. It hands back a confident looking matrix and a warp that still looks plausible. 6.5 pixels off, delivered without a complaint. The unit sphere doesn't have that blind spot. Every direction has a representative on it, including the ones with a 0 in the corner. That's the real reason the SVD is the default. Not that it's fancier, but that it never assumes something about the answer before it's found it.
Let's watch it work. These 4 green corners are the only input. The right-hand panel is the actual warp, every pixel of it, computed from the H those 4 points determine. Nothing here is a preview, it's the real transform. Watch what happens when I drag one corner. The whole plane follows. Not the corner, the whole plane, because H maps every point, and I only ever told it about 4. Now watch the readout at the bottom. I'm holding out a 5th point, the center of the plane, and checking where H sends it. On a flat scene, it lands exactly where it should, 0.0 pixels. Keep an eye on that number. In 2 minutes, it's going to tell us something the picture won't. Before that, the step that every textbook mentions in a footnote and every working implementation treats as mandatory. Your points are pixel coordinates, 402, 311, and then a 1 because they're homogeneous. Look at that vector. 2 of the numbers are in the hundreds, and the third is 1. And in the matrix A, some columns are built from products of coordinates, so they're in the hundreds of thousands. One matrix, columns spanning 5 orders of magnitude. That's not a stylistic problem, it's a numerical one. The condition number of A tells you how much the solve amplifies noise, and here it's about 4.5 million. Your correspondences are good to half a pixel, and your answer isn't. The fix is one paragraph of code, and it's called Hartley normalisation. Shift the points so their center is at the origin. Scale them so their average distance from it is √2. Solve. Then undo the 2 shifts on H at the end. Same points, same algorithm, condition number 4. That is a factor of 1,000,000 for about 6 lines. Do not skip it. 2 ways this falls over. Neither of them announces itself, and that's what makes them worth knowing. The first, remember the rule, no 3 points on a line. Here's what it actually means. 4 points spread out. The rank of A is 8. We have 8 independent equations, and H comes out. Now slide 3 of them onto a line. Rank 7. 2 of those 8 equations have quietly become copies of each other. 7 equations, 8 unknowns. H is not determined. And notice what that is not. It isn't rounding error, and a better solver won't rescue it. The geometry genuinely does not contain the answer.
It's also why RANSAC throws away collinear samples before it calls the solver rather than after. The second is nastier. The whole derivation rested on one assumption: the scene is a plane. So what happens when it's nearly a plane? A brick wall that bows, a book that isn't quite closed, a table with something on it. You still get an H. The solve doesn't fail, nothing warns you, and the warp still looks plausible. That's the danger. It looks like it worked. Which is why you hold a point out. Take a fifth correspondence, don't give it to the solver, and check where H sends it. On a plane, it lands where it should. On a scene that isn't flat, it doesn't. And that number is the only thing that will tell you.
So the whole thing on one screen. X prime is similar to HX, one plane, any two views. 8 degrees of freedom because scale is free. Cross product to kill the scale, which makes it linear. 2 rows per point pair, 4 pairs, stack them into A. Smallest singular vector with H normalized, and normalize your coordinates first. That's every flat thing you've ever straightened in a photograph. Every panorama you've ever shot. And the reason a phone can turn a photo of a page into a scan. One last thing, and it's the honest one. Everything today assumed your 4 correspondences were correct. In real images, they come from a feature matcher, and some of them are simply wrong. And least squares has no defense against that. One bad match, and it will confidently hand you a completely wrong H. Which is the next video, RANSAC, and how you fit a model when some of your data is lying to you. See you there.